A membrane potential is the difference in electrical charge between the two sides of a membrane. This membrane potential or charge difference across the membrane is ultimately caused by ion concentrations and the difference in ion concentration between the outside of the cell and the inside of the cell. So this chart shows the typical ion chemical or concentration gradients across the plasma membrane. And as you can see, the primarily extracellular ions are sodium and chloride, while the main intracellular ion is potassium. And if we look at that distribution in a cell, inside there are all of these positively charged potassium ions, and they're balanced by negatively charged anions, which inside the cell are mainly proteins. And outside of the cell, there are lots of sodium and chloride ions. So you can think of the cell like a banana floating in the ocean. It's full of potassium in a sea of sodium and chloride. And it's that differential distribution of ions across the plasma membrane and the membrane's permeability to those ions that determines the membrane potential in a cell. And that separation of charges across the plasma membrane is extremely powerful, as we'll see. So voltmeters are able to measure the difference in voltage between an intracellular electrode and an extracellular electrode. The extracellular electrode is always the reference point, and we measure the intracellular voltage compared to that extracellular reference. And in living cells, there's this collection of negative charges inside the cell. So living cells have a negative membrane potential, which can be written as V sub m for membrane voltage, or E sub m for membrane electromotive force. Then if we look at this panel here on the bottom, we can see where a voltmeter has been used to actually record that membrane potential. In this region before the star, both of the electrodes, the red recording electrode and the black reference electrode, are both in the extracellular fluid. And so the recorded potential is 0 millivolts. There's no difference in the voltage detected by the electrodes. But at the star, that red recording electrode is inserted into the cell, and a membrane potential of about -70 millivolts is recorded. So the inside of the cell is negatively recharged with respect to the outside of the cell. And at rest, this voltage is stable, and this negative resting membrane potential exists because of that tiny excess of negative ions inside the cell and the tiny excess of positive ions outside. So it's important to remember that here we're measuring the difference in charge across the membrane. And this measurement doesn't tell us anything about the absolute number of negative and positive charges on either side of the membrane. So we can set up a model system like this to look more closely at where that membrane potential or that voltage difference between the inside and the outside comes from. And just like we saw in the last cartoon, here we have two microelectrodes, one intracellular and one extracellular, that can record the voltage across the membrane that will be reported on this voltmeter. And if we zoom in on this area of the cell-in-cell membrane, we can look at those compartments more closely, the inside and the outside. And we can see that there's a difference in ion concentration between the compartments. And we can zoom in even further to look more closely at those ions. So here we've zoomed in further and we were looking at the ion gradients in this hypothetical model system. And we see that on the inside, there is high potassium and high negatively charged anions, which we said are mostly proteins in this inside compartment. There are also a few sodium ions scattered around, but it's mostly potassium as well as those anions. And on the outside, there are a lot of positively charged sodium ions and negatively charged anions, which in this compartment are mostly chloride. There are also a few potassium ions as well as other positive cations as well. So let's just say that in this hypothetical system, our condition is an impermeable plasma membrane. So no ion channels are open and no ions can move between the compartments. And the way we have this set up is so that the charges are balanced. So that means that if we turn on the voltmeter, the voltage is 0 millivolts because there's no voltage difference between the inside and the outside of this cell in this model system. And now we can use this model system to look at how ion concentration gradients and opening ion channels creates a membrane potential. Now let's look at what happens to the membrane potential in this model system when we open some potassium channels. We already saw that there's this potassium chemical gradient or concentration gradient already in place with high potassium inside and low potassium outside. So opening potassium channels would cause potassium to flow out of the cell with its chemical or concentration gradient. So potassium is moving from inside to outside. And the movement of these positively charged potassium ions without any accompanying anions means that now there's a charge difference or an electrical gradient. Since positive charges are leaving the inside, there's now a negative charge inside, which means there's a negative membrane potential. And that inside negative charge starts to oppose the force of the chemical gradient, and then movement of potassium from inside to outside slows, and as we'll see, it eventually stops. So now let's look at what we just saw in words in our model system. So first we said we would open some potassium channels. And there's this large potassium chemical gradient or concentration gradient in place where the inside of potassium concentration is much higher than the outside potassium concentration. And that large chemical gradient or concentration gradient causes diffusion of potassium with its gradient from the inside to the outside. And that diffusion of positive potassium ions down the chemical gradient without accompanying anions produces a voltage across the membrane that can be measured on this voltmeter. There's a loss of positive charge from inside the cell, which means the inside is slightly more negative now than the outside, and that difference in charge between the inside and outside is the membrane potential. Eventually, the negative membrane potential generated by potassium diffusion from inside to outside begins to oppose the force of the chemical gradient, slowing and eventually stopping further potassium diffusion. And this is because the positively charged potassium is attracted back inside by the negative charge it left behind, and because the positive potassium is repelled by the positive charge it generates outside. So the bottom line is that at first, diffusion is the dominant force driving the movement of potassium ions across the membrane from inside to outside. But as the inside of the cell becomes more negative, that negative electrical force pulls the positively charged potassium back inside. So when does potassium stop flowing down its concentration gradient? Well, that flow stops when the force of the electrical gradient is equal to and opposite the force of the chemical gradient. So as we saw, ions, the potassium ions, flow down their chemical gradient, creating this negative membrane potential. And eventually, that potential difference is equal to and opposite the concentration gradient or the chemical gradient. And this is called the equilibrium potential for the ion, where this is the equilibrium between the electrical and chemical forces, and therefore there's no net movement of the ion. And that equilibrium potential can be calculated for each individual ion using the Nernst equation. It's also important to note here that at the equilibrium potential, the overall concentration of potassium inside and outside has not changed. And that's because very few ions actually have to diffuse across the membrane to reach this equilibrium potential. So there's not a measurable change in ion concentration. So this is the Nernst equation, and it just converts a concentration difference for an ion between the inside and the outside of the cell into a voltage. And the voltage calculated by the Nernst equation is just the voltage difference across the membrane, or the membrane potential, that is equal to and opposite the concentration gradient. So at this voltage, there's no net movement of the ion. And here we're calculating equilibrium potential in millivolts for a given ion X by taking this constant of 60, which takes into account the gas constant and absolute temperature and Faraday's constant. And we're dividing that constant by the charge of that ion and multiplying that number by the log of the concentration of the ion on the outside divided by the concentration of the ion on the inside. Sometimes this equation is also written as negative 60 over Z times the log of the internal over the external concentration. So that negative just flips the outside and the inside, but both give the same result, but just be aware of that. So the Nernst equation gives us the equilibrium potential for any given individual ion. However, most membranes aren't permeable to only one ion. They're typically permeable to multiple ions, and not only that, but ion permeabilities of a membrane can and do change depending on the situation. But we can still estimate the equilibrium potential of these more complex and dynamic biological systems and biological membranes if we consider the factors that are important in determining membrane potentials. And those are ion gradients across the cell membrane, driving diffusion of ions down their chemical or concentration gradient, and the relative permeability of the membranes to those ions. So if the membrane is permeable to more than one ion, then the ions that are more permeable will contribute more to the membrane potential than those that are less permeable. So the way we're able to calculate this membrane potential when the membrane is permeable to more than one ion is by using this Goldman-Hodgkin-Katz or GHK equation. So here we're taking into account multiple ions and their concentration gradients as well as their relative permeabilities to calculate this resting membrane potential, which is really just the steady membrane potential in the cell at rest when it's not producing an electrical signal. And to calculate this membrane potential, we just take that same constant of 60 multiplied by the log of the permeability of each ion times the ion's concentration outside the cell, divided by the permeability of the ion times the concentration of that ion inside the cell for each ion. Now, if we look at the resting membrane potential of a typical excitable cell like a neuron or skeletal muscle cell, we can take these principles into account and estimate their resting membrane potential. And we know the important things to think about are the concentration gradient and the permeability of each ion. So at rest in excitable cells, some sodium channels are open and some potassium channels are open. So we know that the resting membrane potential must be somewhere between the equilibrium potential for sodium, which is around positive 59 millivolts, and the equilibrium potential for potassium, which is around negative 85 millivolts. So it has to be somewhere in this range. We also need to take into account how permeable the membrane is to each of these ions. And it turns out that at rest, the permeability of the membrane to potassium is 25 to 30 times greater than the permeability of the membrane to sodium. So since ions that are more permeable contribute more to the membrane potential than those that are less permeable, we now know that the resting membrane potential is between the equilibrium potential for sodium and the equilibrium potential for potassium, but it's much closer to the equilibrium potential of potassium. And this is true. The resting membrane potential of excitable cells is generally between -40 and -85 millivolts.